Yeah, so let me begin by first thanking the organizers for inviting me to present our work. So before going into our technical details, let me show you a glimpse of our campus. I'm from IIT Mandi, and not very far from here, we have a very nice campus. We're in the foothills of Himalayas. If you have not been to this campus, I personally invite you to come here. We have a good monsoon there, and we also have snow in the campus. Not inside the campus itself, but a bit far away from the campus. So, however, I shall be talking of systems which are much lower than these temperatures. So, if you put yourself or try to imagine the temperature of the sun out here, and here is somewhere in the room temperature. So, I'll be talking of systems which are much lower than these reference temperatures, and I'm talking of this state of matter called the Bose-Einstein condensate, and the temperatures generally discussed in these regimes are of the order of nanokelvins. So this is a famous BEC image that you can see all around. This is the famous 2D velocity distribution of the bosonic atoms, and for which the Nobel Prize was awarded back in, the first experimental achievement was done back in 1995, and since then it has been 30 years since the first BEC was experimentally achieved. And within these 30 years, we have seen a lot of progress from the theoretical side as well as the experimental side. So it has been like 30 years in the experimental achievement of BEC. So now, and we have seen a lot of progress more on the experimental side and the theoretical sides. And this is, according to my opinion, is a field of science where the experiments and the theory go both well hand in hand. And now, over the last few years, the most important focus of this type of Bose-Condensed systems has been on the quantum technology side. And there are four basic pillars on the quantum technology, mainly quantum simulation, quantum sensing and metrology, quantum computation, and quantum communication. So in the quantum simulation side, BEC systems are now being used as quantum simulators for real condensed matter materials. The BEC systems or the cold atomic systems are also being used to make ultra precise sensors in atomic clocks for navigation purpose, let's say, or even for matter wave interferometers. In the last couple of years mainly has seen the development of this neutral atom quantum computing by this company called Cold Quanta, and also we have quantum communication using these Bose-Condensed systems. So now what happens in a BEC, or how is a BEC achieved theoretically? So one starts off from a thermal gas of bosons. The temperature is lowered down. The de Broglie wavelength of each of the associated particles becomes larger because it is inversely proportional to the square root of the temperature. And when this wavelength becomes comparable to the interparticle separation, the wave functions or the wave packets of each of the particles start overlapping with each other. And we get a macroscopic wave function of the Bose-Einstein condensate. From a classical point of view, if you think of this Maxwell-Boltzmann's velocity distribution, the red curve is at a very higher temperature, and think of doing an evaporative cooling or a laser cooling, by which are the experimental methods to cool down a thermal gas to form a Bose-Einstein condensate. So by these cooling procedures, imagine that these highly energetic atoms are being blown away. The system is being, so as you cooling down the temperature, these highly energetic atoms are being blown away, we let the system rethermalize, and we get the most number of atoms peaking around a very small velocity. And this was essentially the first BEC image that I had shown initially, where you cool down thermal atoms and you get the most number of atoms peaked around a very small velocity. So to put things into perspective, we are talking of energies, very low energetic systems. The Bose-Einstein condensate lying at the lowest most energy scale, and the high energy physics, as you know, deals with much higher energy scales. About the density of matter, the BECs are very dilute in nature, while we talk of solids, gas, and liquid, which have interatomic separation of the order of 10 power minus 8 centimeter, minus 7 centimeter, minus 8 centimeter roughly. We have a separation of around 10 power minus 6 to 10 power minus 3 centimeter. In a BEC systems of the order of 10 power 9 to 10 power 14, compared to even gas at normal room temperature and pressure, which is about 10 power 19. So in that sense, the BC systems are much diluted in nature, so the interatomic separations are much larger. So now we have to remember in a very nutshell that we are talking of systems which are very lower in energy, they are much diluted in nature. We're talking of temperatures of the scales of nanokelvin, and of course that energy is in the lowest most energy scale that I had shown you in the earlier slide. About the size of the matter, if you are comparing to a football field, the Bose-Einstein condensers are few micrometers comparable to a strand of a hair, let's say. So till now, the group 1 alkali elements have been cooled to degeneracy, and these are the sodium, potassium, rubidium. And also we have something called the dipolar BECs, in which people take these transition metals, chromium, dysprosium, or ytterbium. And also people are now talking of mixing these two atoms to form a multi-component Bose-Einstein condensers, which is the topic of our study for today's discussion. So in our group, we mainly do research activities connected to weakly interacting systems and strongly interacting systems, both in the closed nature and in the open quantum nature. So for today, I will be mainly focusing on weakly interacting quantum gases, both in the open system settings and the closed system setting. So as I was telling, our main motivation of study or today's discussion is Bose-Bose mixtures, and the BECs for which the BECs of dilute interacting atomic gases have already been achieved, and we have also achieved the multi-component condensers with the experimental tunability to tune the scattering lengths by a method called phase-Buck resonance. So these Bose-Bose mixtures have a very unique feature in the sense that it can admit two phases. So each of the component of the Bose-Einstein condensers have intraspecies interactions as well as interspecies interaction. So depending on the intraspecies and the interspecies, as an energetically favorable solution, you can get a miscible configuration, as in when the interspecies interactions are much lesser than the intraspecies, you get both the condensers overlap in the spatial region, whereas if your interspecies is much larger than the intraspecies, you get them phase separated or in the immiscible configuration, in which two condensers can lie in two different regions of the space. So this is two of those possible configurations in which the condensers can lie either side by side or they can be in a sandwich configuration. Even these phase separated binary condensers, by tuning the scattering lengths, have been experimentally achieved like 20 years back with using atomic species of two different atoms, or also of atoms of very differing masses. So, and this is generally the Hamiltonian corresponding to a Bose-Bose mixtures, and we have the kinetic energy operator, the intraspecies terms and the interspecies terms. So for today's discussions, I will be focusing mainly on two important questions, that is, how does a disordered system choose an ordered state? And the next question that I will try to address, how does a system escape from a metastable state? So at first, let us try to address the question that how does a disordered system choose an ordered state? And for this, let us begin by asking a very simple question, that if you cool down a Bose system across a phase transition point, does the system immediately decide to go to the ordered state? And the answer is no. And this idea lies very much at the heart of Kibble-Zurek mechanism. So what happens is, when you quench down across the phase transition point, there is a critical slowing down. The different parts of the condenser order parameter develop their own local phases, and when they try to coalesce, the defects inevitably appear at the interface walls of the domains. So for this work, we quench down the vacuum, or try to increase the condensate density to look at the growth of these binary condensers, both in the miscible regime and the immiscible regime, and try to look at how does these defects appear during the phase transition dynamics, as well as how the phase separation occur during the phase transition dynamics. And not only we count the number of defects, which is actually the Kibble-Zurek mechanism, but also try to address the question that how does these defects orient themselves on the space. So for which we use the stochastic Rossby-Zariski equation, And if you know, then this part of the stochastic Ross-Piravitsky equation is the usual zero temperature Ross-Piravitsky equation. So the modeling stands in this way, that we have a coherent region marked by this psi. The stochastic Ross-Piravitsky equation essentially looks at the dynamics of the coherent field. This coherent field is now exchanging atoms and energy with the incoherent regime. The incoherent regime is modeled by the thermal noise eta, the chemical potential mu, and the temperature T. And we also have a dissipation parameter gamma and the thermal noise eta. So the etas are essentially the Gaussian white noise, which is delta delta correlated in space and time. So the idea of using this stochastic Ross-Piravitsky equation is to mimic an experimental condition. So in experiments, both noise and dissipation will be there, and we need to see the growth of the condensate experimentally, where the fluctuations and the noise are very inherent to the system. So what we do numerically, and the key numerical experiment for us, is to quench the chemical potential in a linear fashion, where we know the final chemical potential, we know the initial chemical potential corresponding to a highly symmetric phase, because as I was telling that when I'm going through a phase transition point, I need to break the symmetry from a high symmetric phase to a broken symmetry phase. So as I do this from mu y to mu f, my tau q is a quench time. So depending on the tau q, I will show you the Kibble-Zurek scaling laws, which are already known, and we want to try to verify this on the binary Bose-Condens systems. So let me play this video. Yeah. So you see what you are trying to do. Look at this, both the densities of the two components, and looking at the number of atoms. So here, and you see the vortices getting appeared on the spatial configuration, and we count the number of vortices at this point. So this point is called the equilibration time, or the point of interest in which the vortices course become clearly visible, because as you are increasing the density, the healing lengths are very large. And if the healing lengths are very large, and the vortices are not resolvable. So in the Kibble-Zurek law, there is something called the freeze-out time. And the freeze-out time in this protocol is not an ideal way to look at the vortices. However, we choose an equilibration time which is proportional to the freeze-out time, and we can count the number of topological defects, which are the vortices in this case. So in a similar way, I can quench the chemical potential to attain a phase-separated binary condensate. So we start off a very small density, we quench the chemical potential to see the growth of the condensate density, and you see the domains appear. And we shall be counting the number of domains in this case and show them that they indeed follow the Kibble-Zurek scaling laws. So here I show this sample condensate norm versus time, and these colored curves corresponds to different quench rates. And the Kibble-Zurek law tells that depending on the quench rates, you have a scaling law of this equilibration time to this tau q. So you see in the z, the dynamical critical exponent times the static critical exponent in this kind of mean field theory is 1, and it should be 0.5 in this case. And if you look at this equilibration time versus the tau q, and I remind you tau q what the quench times in which you are using for quenching, they bear a very nice, excellent Kibble-Zurek scaling law, and we find 0.48 in this case. Now moving ahead, we can do also analytical calculation on the top of these numerical simulations. For this, we drop the spatial dependent terms and also the noise, and we find that the condensate norms bear very nice analytical expressions in which you get a very nice agreement with the analytical curves and the colored curves. We now look at essentially the number of vortices in the miscible case, and the number of vortices you see, they vary with the tau q. So the more slow you quench, you get lesser number of vortices. The more faster you quench, you get larger number of vortices. And for very fast quench regimes, you get a deviation from the Kibble-Zurek scaling laws. The domains are also being counted here. However, for counting the domains, we actually look at the domain centroids, and also it bears a very nice Kibble-Zurek scaling law for us, for which it turns out to be 0.48 and 0.49. This 1 and 2 represent the number of domains in one component and the number of domains in the other component. Similarly, V1 and V2 are the vortices in one component and the vortices in the other component. And they numerically find that they bear very nice Kibble-Zurek scaling laws. we do not stop at only counting the number of defects, but we also ask the question that what is the geometry of these topological defects, or in particular the domain walls. So what is the length of the domain wall? Does it scale over the quench rates? And the answer is yes. So we see very nice self-similar dynamics at this time window, in which we find the domain coarsening to to scale very nicely with the quench rates. We also compute the area of the domains, and with the area of the domains also bears a very nice scaling law with the quench times. As I was telling, we do not only stop at counting this number of defects or the geometry, we also now ask the question that how these vortices are spread over the region of the space. Okay, so in a 2D, how are the vortices are spread over the region of the condensate, and for which we compute the pairwise vortex distance, we bin it at this equilibration time, and we find out that the solid curve is the theoretical line corresponding to this famous disk line picking problem distribution, or the Poisson distribution. And also we compute the first nearest neighbor spacing distribution, and it resembles for k is equal to 1 a Wigner-Dyson distribution. So the pairwise vortex distance as well as the first nearest neighboring distance have universal scaling laws corresponding to the Wigner-Dyson distribution as well as the famous line disk picking problem. We can also look at how the domain centroids are spread over the space, and for which again the pairwise centroid distance resembles this line disk picking problem, and for the first nearest neighbor spacing distribution for the domains, they resembles this pairwise function for k equals to 2. Now let me point out, in earlier slide for the vortex, the line was for k equals to 1, however for which here it is for k equals 2. The reasoning is follows, these red things are the densities for one component, and this is a phase separated regime in between two domains of one component the other component is trying to fit in. So for one of these domains, it is the nearest neighbor is always the blue one and not the red one. So for every red, it is encountering a blue at the nearest neighbor and not the red one, because it is in the phase separated regime, for which we get a very nice agreement with the k equal to 2 first nearest neighbor spacing distribution. Now, since this is a conference mainly on real condensed matter materials, let me point out the Kibel-Zurek mechanism has also been observed like 20 years back, not 20 years back, like 15 years back, for a material called ER-MnO3, which is a multiferroic material, and what the authors have quenched down the materials from very high temperatures to low temperatures at different rates, and shown that the number of topological defects in the form of vortices appearing, and they have a very good scaling law with the 3D XY model depending on the quench rates that you have. So Kibel-Zurek mechanism has already been seen in real condensed matter materials, and recently people have also done numerical simulations in the case of barium titanate, where they also claim they have looked into the Kibel-Zurek scaling of this non-equilibrium phase transition. Now, after having answered this question that how does a system choose an order state, let me try to address another problem. How does the system escape from metastable state? For which I actually mean something called a phenomena called a false vacuum decay. So in a false vacuum decay, what happens is that you have an underlying asymmetric double well potential like this, and this is the metastable state, or in the field theory language we call it is a false vacuum. And the idea is to look at the rate of decay of this false vacuum to the true vacuum marked here. So now in the context of the early universe, Sidney Coleman in these two of his papers claimed or made a very nice study that if this false vacuum decay has to occur, it has to occur through the nucleation of bubbles. And this false vacuum decay is a universal phenomena, and the idea is the following, that the universe that we are in, we are now stuck in a metastable state. We even do not know what will happen if the system actually goes down to a true vacuum. Now this process is again a very highly non-perturbative nature process. It's a non-equilibrium, and the non-linearity of this problem has made direct experimental evidence of these apparent theoretical hypotheses. So the question that was asked is that if it has to occur in the early universe and the energies involved are very high, the time scales involved are also very high, so it is indeed very impossible to predict this. So now the question that one asked is that can we have some analog models to conduct tabletop experiments? And it has been very recently, like back in 2023, that the group from the Trento has experimentally achieved false vacuum decay using a system of coherently coupled condensates. However, the experimental proposal was proposed by Joachim Brand and all these other people back in 2015 in the context of cold atoms, that how does a false vacuum might decay to a true vacuum. So now for this, as I was telling, the system required, or the system that has been used to experimentally achieve or observe this false vacuum decay, is a coherently coupled condensate. So now compared to the system that I was considering earlier, it was a binary condensate, but now these binary condensates are now loaded in two hyperfine states, and these two hyperfine states are being coupled by some linear coupling term of the strength omega. So there is a constant interchange of atoms from this level to the other, depending on the interaction terms and the omega term, which is the strength of the coupling. One can achieve a ferromagnetic condensate, as in one of the states can be highly polarized, or you can have equal number of atoms in both the states corresponding to a paramagnet. So this is the coupled Gross-Pidavitsky equation with a linear term sitting out here. Now these systems, for this system, the number of atoms of the total system is conserved. However, the number of atoms in each of the levels is not conserved, as you can already imagine. So I can always define a magnetization or an population imbalance kind of quantity, which gives you the difference between the number of atoms in the first level and the second level. So the magnetization in this case is my order parameter. So when the particles are all sitting in one of the levels, I will call it as a ferromagnet, and if they're equal in numbers in both the levels, I will call it as a paramagnet. So this is the mean field energy term, and the most beautiful thing of this energy landscape is that you can actually tune this energy landscape from a double well structure to a asymmetric double well potential as is required to observe the false vacuum decay. And this tuning can be done by this detuning term sitting out here, as well as the omega term out here. But before I go on to describe this non-equilibrium dynamics of this false vacuum decay to the true vacuum decay, I think it is important to also understand the systems at finite temperature at equilibrium, for which we have done these studies, charted out the phase diagram from a paramagnet to a ferromagnet as a function of finite temperature and the omega. So while you can already see that depending on your omega and the temperature T, the paramagnetic phase is always favored. Not surprising, but it is just to prove that indeed our system is actually behaving like a transverse phase Ising model system. So now, for which we use this self-consistent Hartree-Fock-Bogoliubov approximation, we first determine the Bogoliubov excitation spectrum, and we compute the thermal density in a self-consistent manner and give proper weightage to the quasi-particle moles depending on the B distribution function. And how did I actually chart out the phase diagram? By computing the dispersion relation. And you see these red lines are the density channels of these systems, and the blue lines are the spin channels of the system. In the paramagnetic phase, where the omega is much larger than the omega critical at temperature equal to 0, you see the spin channel is gapped, however the density channel is ungapped, it is 0. At the critical point, when my omega is exactly equal to the omega sphere, both the density channel and the spin channels are gapless. Again, in the ferromagnetic side, the paramagnetic, the density channel remains gapped and the spin channel becomes gapless again. Now these transitions from the at this 0 temperature can also be looked in the finite temperature case. However, the most important difference that you see, that the omega critical has now shifted to lower values of omega, telling that okay, my paramagnetic phase is much more favored at this high temperature. And these colors are basically the measure of the spin character of these dispersion branches. The Q equals to 1, meaning it is a pure density branch. in the ferromagnetic scenario, you see a hybridization of spin and density channels, and these blues are the pure spin density modes where Q is exactly or very close to -1. This is the transition in the spin gap as a function of temperature, and we see there is a fall of decay of magnetization as a function of temperature. And we also can compute analytically the dispersion relations at temperature T equal to 0. In the trapped case, we see this transition is marked by the softening of the spin breathing mode. So this point is actually the transition from a para to a ferromagnet, and this is turns out by our dynamical calculations is a spin breathing mode for the system. Now, as I was telling about the false vacuum decay, we actually initially prepared the system at this state using the SGP at different finite temperatures, and then we gradually ramp the detuning term as is done experimentally to put this system here. So now this B, this energy landscape B, is actually the energy landscape as a function of magnetization for which I want to see the false vacuum decay process. And now after ramping the detuning to make the system prepared out here, I put the gamma equal to 0 in the SGP in the stochastic Gross-Pedavisky equation and then wait and watch. And what we find is that the decay does not occur uniformly. However, you get local patches of bubbles of the opposite magnetization, and with time when it grows, it actually assumes the true vacuum. So these red colored domains are the actual bubbles that we find in the system. And the question now asked is that what is the rate of the decay with the temperature? Okay, and this is what we want to verify if this thermal instanton theory is actually valid, or are we being able to verify this theory for our systems? And the answer is yes. And what we do is to do these stochastic simulations for thousands number of times, we average it and now try to count the number of realizations that are still in the metastable state. So we ask the question that how many of these fractions of these systems still remain in the metastable state, and that would give an estimate of the metastability of the system as a function of temperature. And you see there are clearly signatures of these exponential decay in the logarithmic curve. And finally, we assimilate all these results and try to show you that for two different values of delta F, as in the final detuning values, I have linear relationships of gamma with these betas in the log scale. And now we have actually verified the thermal instanton theory for these kind of systems. So the main conclusions of this work were actually done by my students in my group. These are the main workflows behind the system. So what we have tried to answer the question is that how does a system choose an ordered state? So this has been recently published in Communication Physics. Then we moved on to a project on this, how does a system escape from metastable state? In between, we had made a detude to learn the system at equilibrium at finite temperatures. And these are the collaborators and the funding agencies. I'm grateful to them for funding us. And then here we are. Thank you. And sorry for all the technical glitches at the outset.
So thank you. Thank you, Orko. You finished it. Thank you, Lord. So is there any questions, comments, some suggestions? Yeah.
So when you say that the number of defects as Kibble-Jurek scaling, and when you are showing that there is domain formation on the other case, so do you have any prediction how the domain grows, like what scaling the domain growth has?
No, Kibble-Jurek does not predict how does a domain grow. There is a different regime altogether.
What I'm asking is that is there a prediction how the domain will grow? I'm not saying it will happen.
Yeah, sure. There is but not by Kibble-Jurek. It's not the Kibble-Jurek mechanism. It's called the domain coarsening, in which you can actually predict how does the domain grow with time. Absolutely is, but not in this time scale. So the domain coarsening is done at a later time scale, which is different from the Kibble-Jurek timing. Of course, it has.
Any other questions? If not, let us thanks again the speaker.